Welcome to this explainer. Today, we're literally popping the hood to see exactly how a backend manages data and scales up to millions of users without, just completely buckling. If you've ever found yourself wondering about the actual architecture powering those high-traffic apps we use every single day, well, you're in the exact right place. We're going to trace the entire journey, starting from basic local system calls all the way up to global cloud load distribution. Seriously, think about this for a second. We interact with these brilliantly seamless apps all the time, right? You open up a social network, you request to see a profile, maybe you process a quick transaction. But how does the code behind the scenes actually parse your request, talk to the database, and stream that data right back to your screen without crashing under the weight of thousands or even millions of other people doing the exact same thing at the exact same time? Well, it takes a beautifully orchestrated stack. To pull this off, developers rely heavily on a magical little concept called abstraction. It's kind of like hiding the complex, oily, complicated engine of a vehicle so you can just focus on, actually driving the car. We don't have to sit there and write raw C++ or interact directly with the machine's kernel just to talk to the operating system. Instead, we simply use APIs and prepackaged modules that execute all those low-level instructions for us, and that frees us up to focus purely on the actual business logic of whatever app we're building. Okay, let's dive into this roadmap. First, the node file system. Second, building an HTTP server. Third, the cloud and scaling. And finally, number 4, routing with Express. Moving right into section 1, the node file system. So the very first big challenge developers run into is manipulating the native file system without writing tedious, low-level machine code. Node bridges this gap perfectly by giving us the FS, or file system module. It's basically a brilliant wrapper around those complex C++ functions, giving your server-side JavaScript the absolute superpower to breeze through file operations. Let's put this into a real-world scenario. Say you're building a server and you need to keep a log of network errors. You'd use fs.writeFile to create that log when the server first boots up. Now, as traffic hits and minor bugs inevitably pop up, you definitely don't want to overwrite that file. So you'd use fs.appendFile to continuously add new error data, maybe tossing in a \n to make sure the logs stay neatly separated on new lines. Later, if you want to archive it, fs.rename easily updates the file name with a timestamp. And to clear out an old log, just use fs.unlink to delete the whole shebang. But hey, a quick word of caution here. Literally every seasoned developer has a horror story about fs.rm. If you trigger a remove command with a recursive flag in the wrong folder, you could accidentally wipe out critical production folders in the absolute blink of an eye. So, with great abstraction comes great responsibility. All right, section 2, building an HTTP server. Now we face the next challenge, taking those local files and sharing that data over a network using client-server architecture. This entire setup works a lot like a continuous, highly orchestrated handshake. Step 1, the client, which could be your web browser or a mobile app, requests specific information via a URL. In step 2, the server, which is our node backend, intercepts that request and parses the details. Step 3, it executes whatever logic is needed. And finally, step 4, it sends back the correct data. It's essentially an infinitely repeating loop. Request, response, requests, response, all communicating strictly over HTTP protocols. Now, to actually make this handshake happen locally while you're building the app, we bind our node process to listen on a specific network port, like port 3000. So what is a port? Think of it basically like a dedicated door on your computer. Your machine has thousands of background processes running at any given second. By explicitly telling our node server, hey, listen on port 3000, we guarantee that when HTTP traffic comes knocking at localhost, it knows exactly which application to talk to. It just guarantees our app intercepts the payload instead of the connection dropping into the void. That brings us to section 3, the cloud and scaling. Frame this massive problem for a second. Your app goes viral overnight, and 3 million concurrent users hit your local laptop's port 3000. And this brilliantly illustrates why a standard machine just can't handle it. It lacks the RAM, the network bandwidth, and the processing power to juggle millions of connections all at the exact same time. The server will hit a massive bottleneck and crash instantly. To actually survive a traffic spike like that, you have to move from your local fixed hardware up to a distributed, elastic cloud environment, which can handle well over 1 million concurrent users seamlessly. So, instead of relying on your physical laptop, you deploy your backend using a service like an Amazon Web Services EC2 instance.
People say deploying an EC2 instance in the cloud, and it sounds super abstract and honestly kind of intimidating. But at the end of the day, it's literally just a rented computer sitting somewhere near Delhi or Virginia in a massive climate-controlled data center without a monitor attached to it. That's it. But here's the magic. Unlike your static laptop, this environment dynamically grabs more RAM and allocates extra CPU cores to absorb the immense shock of traffic. It's a real game changer.
On to Section 4, Routing with Express. Even with that robust cloud hardware, managing thousands of different HTTP endpoints manually with raw Node is just a clunky nightmare. You'd be forced to manually parse URL strings, extract headers, and write so much repetitive code. To fix this, developers introduced another amazing layer of abstraction, the Express framework. Express sits neatly right on top of that native HTTP module and completely streamlines things like error handling and, most importantly, routing, turning total chaos into elegant, simple routing functions. Here's how it flows. When someone types in a domain name, the internet resolves that human-readable name down to your specific AWS server's IP address. And yes, the IP address gets the traffic to the server, but it's the specific route, that path at the very end of the URL, like /about or /profile, that tells your Express application exactly what data block to fetch. Express cleanly reads that route and instantly directs the user's request. Section 5, the modern backend lifecycle. Let's move to and see how this builds together into the ultimate big picture. Let's rapid fire through the exact chronological path a request takes, tracing it right from the browser click down to the database and back onto the user's screen. At 0 milliseconds, a user clicks to see their profile. By 10 milliseconds, DNS translates that domain into an IP address. At 20 milliseconds, traffic arrives at your highly scalable cloud server. Moving to 30 milliseconds, your Express app intercepts the /profile route. At 40 milliseconds, it queries your database, and finally, by 50 milliseconds, it grabs the exact data payload, slaps on the proper HTTP status codes, and streams it right back to be beautifully displayed on their screen. And there you have it. You've learned how to scale from basic system calls on a tiny local file all the way to a globally distributed cloud architecture. But as you digest all of this, here's a final provocative question. With millions of requests constantly hitting your newly robust cloud server, how do you prevent your database from becoming the ultimate bottleneck? Think about how you structure that back-end data, and we will catch you in the next explainer.